All right, we are going to look at how to do a one-way ANOVA test. So ANOVA stands for Analysis of Variation. Here's where we get the AN, the O, and then the VA that represents ANOVA. And what this allows us to do is it allows us to test the equality of 3 or more population means by looking at some sample variances. So up until this point, all of our hypothesis testing that we have talked about have only allowed us to compare at most two different populations to each other. Well, if we need to look at 3 or more population means, we would do an ANOVA test. Now, one thing to be aware of is that if it turns out that the equality of the means is rejected, this does not tell us which of the means was not equal. We would then have to proceed with some other tests in order to decide which of the means was not equal. So now one-way ANOVA is used when the population is characterized by only one factor. So we can only be looking at one variable at a time for our different populations. And then we are also going to be using an F distribution when we use ANOVA. So that just means we're going to be using a different standardized table when we look up our critical values. Now, to set up our hypothesis test, first of all, our requirements. Again, we have to have a random sample. Now, we want to make sure that our populations are independent from one another. We also have to make sure that they are categorized by only one factor. So we're only looking at one treatment at a time. And we would like our populations to be approximately normal. Now, this is considered a loose requirement because it's not absolutely critical for them to be normal. So if they're slightly skewed, we're still going to be able to do our ANOVA test. And then another loose requirement is that the variances of the populations are equal. And again, this one isn't set in stone or that critical because our ANOVA test will still work pretty well as long as our variances for the populations are equal or are close to being equal. So now when we set up our hypothesis testing, after we've checked our requirements, we're going to look at our null hypothesis. And our null hypothesis is that population 1, or the mean of population 1, equals the mean of population 2, equals the mean of population 3, etc., 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 until you get to however many populations you're testing. And then our alternative hypothesis is that at least one of the means is not equal. And now again, this test doesn't tell us which mean is not equal. It just will indicate whether or not they are all equal or if someone is not equal. Now the good news for this section is we are just going to use StatCrunch to find this. We can still find our test statistic and our p-value using StatCrunch. We're going to go to the Stat menu, to the ANOVA menu, and then to the one-way menu. Now, if you are going to do the test statistic and still use the critical value method, so you would go to the standardized F distribution, there are 2 different degrees of freedom for the F distribution. So you would have to look or to compute the degrees of freedom of your numerator, which is going to be k minus 1, where k is the number of samples. And then the degrees of freedom of your denominator is n times k minus 1. K is still our number of samples, and then n is the sample size. So if you still choose to look up your critical value by hand, as opposed to using the p-value method, you're going to have 2 different degrees of freedoms that you'll have to work with when you are using the standardized table for the F distribution. So let's do an example here. Let's say that we want to test if different fertilizers change the level of nicotine in leaves of tobacco plants. So the following table shows the level of nicotine for each plant in a particular experiment. So I have no fertilizer, fertilizer A, fertilizer B, fertilizer C, and fertilizer D. And then the numbers in here show us the level of nicotine for each plant that was in each category. So now, first thing we want to do is we want to check our requirements. So Whether or not it was a random sample, again, we don't have anything in the problem that indicates it was not random. So at this point, we would have to make the assumption that the plants were assigned to the different fertilizer groups randomly. Now we have to check for independence. So we are going to make the assumption that if they were in the no fertilizer group, they absolutely had no fertilizer. So they didn't get any remnants of A or anything like that. So everything would be independent of the other categories. And then we want to make sure that it's categorized by one factor or treatment. Well, the only thing that we changed, according to this experiment, was the fertilizer that they got. So we're going to assume that the amount of water they got and the temperature and the amount of light and all those other things, we're going to assume that that was controlled. Okay, then we want to try to decide if the populations would be approximately normal. Well, if we know anything about just general plant growth, most plants growth have a normal population. So you'll have some that are short, some that are tall, and you'll have a whole bunch of plants in the middle that are, about the same size. So plant growth in general typically follows a normal population. And then the variances of the populations are equal. Again, we don't really have enough information at this point to determine whether or not that one is true. So we are going to make the assumption that it is true. So now that we have checked all of our requirements, we are going to go ahead and set up our null and our alternative hypothesis. So my null hypothesis would be that the mean of no fertilizer was equal to the mean of fertilizer A, which is equal to the mean of fertilizer B, equal to the mean of fertilizer C, and equal to the mean of fertilizer D. I just used these subscripts in here to indicate the type of fertilizer that we had. We could have just put 1, 2, 3, 4, and 5 in there if we had wanted to. Our alternative hypothesis is that at least one of the means is not equal. And again, this won't tell us which mean. It'll just indicate whether or not we need to continue doing more tests to figure out which mean is not equal or not. So now we're going to go ahead and we're going to go into StatCrunch, and we're going to find the test statistic and the p-value, and we're going to go to the menu Stat, ANOVA, and then One Way. So as you can see, I have StatCrunch opened up, and I have all my information from the sample problem added in here. I have my headings up here to represent which category they were in, and then each of the corresponding data values. So now to do the ANOVA test, I'm going to go to Stat, ANOVA, One Way. Now the first thing it asks me to do is to select the columns. So my columns that I select, I need to make sure that they have the data values in there. So I have data values in all 5 of these columns actually. And then I actually will not need to select anything else. And I go with compute, and it gives me this printout, which down here, it will tell me my test statistic, which ends up being 12.748, and then my p-value, it tells me, is less than 0.0001. So now this is where you would have the 2 options. You could go to the standardized table, and you could look up what the critical value is for this particular example, and we could compare the critical value to the test statistic, or you can use the p-value method, where you would compare your p-value to what your significance level is. Either method that you choose will give you the same results. Now, I don't think in the example I specified in a significance level, but whether our significance was the 0.05 or the 0.01, our p-value is less than both of those. So in this particular example, we would be able to reject the null hypothesis that all of the means are equal. So that gives us an indication that out of the no fertilizer, fertilizer A, B, C, or D, at least one of them had a different mean than the others. Now again, it doesn't tell us which mean is different, it just tells us that one of them is different. So if I look up here where it has all my information and it shows me the means, I don't know if the category here of none was low, or if maybe the category of B was high. So this test does not tell me which mean is different, it just tells me that one of the means was different. If we needed to figure out which mean was different, then we would need to do some post-testing that would allow us to figure out which of the means is actually different from the others. Alright, so what we looked at in this video was what a one-way ANOVA test is, what it does for us. And then we looked at how to set up a hypothesis test for it. So we looked at the requirements, what the null and the alternative hypothesis would look like, and then we looked at how to use StatCrunch to find the test statistic and the p-value.